Hi, I'm Victor,
I'm Alex.
and today we're going to be presenting on the 2003 Nobel Prize in Medicine or Physiology, granted to Paul Lauterbur and Peter Mansfield. So, this Nobel Prize was awarded for both of their groundbreaking discoveries in the field of magnetic resonance imaging, or MRI. Now, of course, I'm sure many of you have heard of MRI. We use it in many of our hospitals and research facilities, and it's been pretty instrumental in modern medicine for diagnosing many different disorders, as well as studying the brain more effectively and other parts of the body. So, uh, Latterber introduced the concept of magnetic field gradients to create spatial images in MRI, and Mansfield was recognized for introducing the concept of slice selection in MRI and pioneering the development of echoplanar imaging, which is a fast MRI technique. So, to give a brief sort of timeline on NMR spectroscopy and MRI, starting in 1937, we have Isidore Isaac Rabi, who measured nuclear spin, followed by Felix Bloch and Edward Mills Purcell's measurement of nuclear precession in 1946. Then the application of Fourier transform in 1966. And then we have Latterber's publication on the first nuclear magnetic resonance image in 1973, as well as the introduction of fMRI in 1990, which we'll touch on later. And nowadays, we have the integration of MRI with other imaging modalities, such as positron emission tomography, which we now know is a PET scan, and computed tomography or a CT scan. So, to give a little bit of background on spin dynamics and the principles, the guiding principles behind them, uh, whenever we're discussing nuclei with non-zero spins, when we apply an external magnetic field, these nuclei will start to precess, or their axis will sort of rotate about this external magnetic field. And so the dynamics of the net magnetization is given by the Bloch equation here. But what we really want to take away is from the Larmor equation, which tells us that the rate of precession is proportional to the magnetic field strength. So in order to actually get a signal from our nuclei, what we want to do is a pulse acquire experiment. So to put it simply, we take an RF pulse and then we use that to tip the net magnetization into the transverse plane for our nuclei. And then we acquire the signal generated by the magnetization precessing in the transverse plane. So once we have our signal, which is given from the magnetization precessing in the transverse plane, the signal is actually composed of the decaying oscillation of these nuclear spins, which we call the free induction decay, or FID. And so we can then mathematically take this FID and apply the Fourier transform, which allows us to extract the frequency components and give us our more legible spectra. And so as it turns out, any of these FIDs, for instance, or really any 1D signal function, can be represented as a sum of sines and cosines. And this matters because when we move into 2 dimensions, we can take any 2D image and construct that out of a sum of plane waves, which is very useful for our actual MRI imaging. So to talk about the relaxation of these magnetic spins, so after the spins are excited, the net magnetization will then slowly be restored to its equilibrium magnitude and orientation. So we have a time constant for the recovery of longitudinal magnetization, which is called T1, and a time constant for the loss of transverse magnetization, which we call T2. And so really, for a long time, magnetic field inhomogeneities were assumed to be a nuisance in NMR, and we spend a lot of time to try and get rid of them. So, for example, I'm sure all of you have seen NMR spectrometers, which poorly shim a spectra. But really the breakthrough idea here that Latterber and Mansfield both recognized was that these controlled distortions of the magnetic field could be utilized for imaging applications. And their fundamental work really laid the foundations for MRI, which we know today. So to give some differences and comparisons between NMR and MRI imaging. In NMR, we have a much higher or much greater magnetic field strength, which isn't really ideal for MRI since we don't want to use such high magnetic fields or such strong magnetic fields in places like a hospital. And then in terms of the gradient coil, we can see that in NMR, these are actually really small. In contrast to in an MRI machine where the coil goes all the way around the patient. And so it's a lot bigger. And the nuclei that we're actually looking at in NMR, they can be any nuclei with non-zero spin. So, we can have hydrogen, carbon, fluorine, all that. But in MRI, we're almost exclusively looking at protons in water molecules.
All right, so now that we have the background, I kind of want to take a little bit step back and see, what does it actually take to generate an MRI image such as this brain right here? So what do we need to do? First thing, we need to be able to excite and or detect only nuclei that are within a single slice of the body. So you can see in this image, we're not detecting any nuclei from below or above that slice, just that slice. And so we do this by a concept called slice selection. The second thing we need after we've excited spins in a single slice is that we need to tell where in the slice the signals are actually coming from. So for example, nuclei here need to be localized to this position, nuclei here need to be localized to this position, so on and so forth, right? We can't just aggregate them all together, then we would not know where in our slice the signals are coming from. The third thing is we need to be able to contrast the different tissues. And so we need to have a different amount of signal coming from different types of tissues so that we can tell where the boundaries are and therefore be able to tell anatomical features and such. So as we mentioned before, Lauterbur and Mansfield both independently had the idea of using gradient coils, such as this one pictured right here. This is what a gradient coil actually looks like. And essentially, when you run current through gradient coils, you vary the magnetic field linearly with respect to some direction. So for example, if you turn a Z gradient coil on, then the main magnetic field will not just be the B naught field, but in fact, it's going to be B naught plus some adjusting factor depending on what Z coordinate you're actually at. And so this was the fundamental idea for slice selection. So let's take a three-dimensional sample here, and let's apply a Z gradient to that. So that means that at each different value of Z, there's going to be a different magnetic field strength. And therefore, the nuclei at each value of Z have a different Larmor frequency, if you remember back to the Larmor equation. This matters because we can actually take an RF pulse and we can have the frequency of that RF pulse exactly match the Larmor frequency of one of these planes in one particular Z value. So that say if we choose the RF pulse to have exactly this frequency here, then we're only going to be exciting the spins in this blue plane, and we're not going to be touching the spins in any other plane because they have a different Larmor frequency. So again, this is called slice selection. This was Peter Mansfield's contribution to MRI. So that's slice selection. We've excited the spins in a single slice. Now, how do we get the spatial location of each spin within that slice? So we turn to two things called phase encoding and frequency encoding. And so essentially, we're going to use the same thing with gradients, except with a gradient that's perpendicular to the slice selection gradient. So for here, we're just going to use the X gradient. And so we're going to consider our blue plane again. Notice how our spins have been excited into the transverse blue plane like so. Now we're going to apply a gradient along the x-axis. So again, a gradient means that at larger x values, you're going to have a higher magnetic field and therefore a higher rate of precession. And so you can see these spins at the larger values of x precess far more than the spins at a smaller value of x, which precess less. So that was phase encoding. So now you notice that at each different value of x, we have phase differences in the actual spins themselves. Next, we turn to the very last direction, which is the y direction, and we apply a gradient along that axis. This is called frequency encoding. And after you provide the frequency encoding gradient, you can see essentially it's the same thing done again. At larger values of y, your spins precess more rapidly than at smaller values of y, because again, the magnetic field is larger here, and therefore the Larmor frequency is also larger at larger values of y. Now, once we've done this, we get this array of spins. Now, what does this actually give us? Well, if we sort of extend our field of view, you might begin to see that this array of spins is sort of has a regular pattern throughout the XY plane. This is actually a plane wave, right? And so essentially what we're doing is we're using field gradients to manipulate the spins in a way to give us any sort of arbitrary plane wave. And so we are going to detect the signal from that plane wave. And essentially what happens is we create different arrays of plane waves by using different phase and frequency encoding gradients. We get the signal from each plane wave, and then we sum up the plane waves, again, using our two-dimensional Fourier transform, which gives us the actual MRI image that we're looking for. So this is actually how the imaging aspect of MRI works. So just putting everything together about the pulse sequences, you can see here, this is called the gradient recalled echo pulse sequence. And this is sort of like the fundamental MRI pulse sequence that all the other complex nuanced pulse sequences can be built off of. And so again, here's our slice selection gradient with our RF pulse. Here is our phase encoding gradient. And finally, here is our frequency encoding gradient with detection of the FID.
Okay, so now that we've discussed sort of how the imaging aspect of MRI works, we can talk about how to further improve our images by leveraging these sort of relaxation kinetics to create higher contrast in the tissues. So protons can have different relaxation times based on a whole host of factors, such as the neighboring groups or molecules or magnetic field inhomogeneities, etc. But the key in order to create this contrast is that protons in different tissues have different T1 and T2 relaxation rates. So now we can take a look at how we can leverage these different T1 and T2 values to create better contrast. So suppose we're imaging a slice and we have two tissues, which are represented by these red and blue lines. And this chart is displaying the transverse magnetization decay of our nuclear spins. So we want to record the overall signal at a time when these individual tissues have different signal amounts. And so, of course, we have two separate areas in which this can take place. So if we record the signal near the start of the T2 decay, pretty much when we create this pulse, then these spins are assuming the spins are at equilibrium. We call this spin density imaging. And if we record the signal after significant T2 decay has already occurred, we call this T2 weighted imaging. And conversely, we can also take a look at the T1 relaxation curves. And so if we excite and then record the signal before the T1 decay has completely finished and gone to equilibrium, we call this T1 weighted imaging. So in order to create these differences or to enhance these differences in between the T1 and T2 relaxation times, we use what are called contrast agents. And so these contrast agents are administered to the tissue that we want to have better contrasts or different relaxation times. And these usually take immediate effect and as such are administered right before or even while the MRI is being taken. And they can be administered in a host of different ways. And so the T1 contrast agents shorten the T1 relaxation time of tissues, which result in brighter signals. And these T1 agents are mostly gadolinium based, such as this gadolinium based compound we have here on the right. And the T2 contrast agents shorten the T2 relaxation time of tissues, resulting in darker signals. And most of these consist of superparamagnetic iron oxide nanoparticles, or spions. However, when we're using these contrast agents, there's going to be some risk involved, despite them generally being benign. And so many of these gadolinium-based agents have been associated with nephrogenic systemic fibrosis, especially in patients with impaired renal function, as their body can't process the gadolinium well, and which resulting in this systemic fibrosis. The spion agents also can result in iron overload, specifically in those with iron metabolism disorders. And both of these can, in very rare cases, result in allergic reactions, which need to be sort of treated on the spot, depending on the severity. And lastly, here we can touch on fMRI, which was developed relatively recently, back in 1990, and fMRI is really just a specialized type of MRI, which allows us to look specifically at the brain activity in sort of more of a functional way than a structural way. And we do this by detecting the changes in blood flow and oxygenation levels. And while this was initially used for research purposes, it was pretty specialized. We've since discovered many clinical applications, which have become increasingly common in order to diagnose and study neurological disorders. And that's pretty much the end of our presentation. Here we have some references, and on the next slide, we have some links if you want to learn a little more about MRI.